Hi, my name is Dignan, and I'm a third-year PhD candidate at the University of Virginia. Today I'm going to talk about applying machine learning techniques to the subject of anomalous microwave emission, or AME. AME is a significant component of galactic radiation that spatially correlates with far infrared thermal dust emission. Currently, AME is believed to arise from rotational electric dipole emission from dust grains the size of a few angstroms. AME is defined as peaking at frequencies from 10 to 70 GHz, potentially impacting massive star formation rates calculated based on the amount of free emission at 33 GHz. However, AME has only been detected in a few regions and a handful of galaxies outside of the Milky Way. So our understanding of exactly what AME is and why it appears where it does is incomplete. Here, machine learning could help us by predicting the probability of an input belonging to a specific class given various features of the input. In other words, what is the likelihood of a given extragalactic region or input to harbor AME, and what environmental conditions or various features make it more likely to do so? To answer these questions, I'm going to train a logistic regression model to predict the probability of an extragalactic region harboring AME. Specifically, I'm using very large array continuum data at 3, 15, and 33 GHz from the Star Formation and Radio Survey, which covers over 300 regions across 30 galaxies at a resolution of 2 arcseconds. As I previously mentioned, 33 of these have been identified as likely AME candidates. 27 of these candidates have additional VLA continuum data at 22 and 44 GHz in repeated 33 GHz observations from a follow-up survey. I will first reduce and image these archival data, then perform aperture photometry to construct radiospectral energy distributions, or SEDs. These SEDs will then be fit to emission models to disentangle the synchrotron free and AME components. From the SED fits, I will measure the relative strength of the AME component, defined as the ratio of the best fit AME to total emission. By doing so at 33 GHz, I will also be able to compare to the star formation rates estimated at the same frequency. For all 353 regions in my sample, I will build a set of parameters that will serve as inputs for a logistic regression model. These parameters will be the strength of the AME from SED fitting, flux densities from archival optical and infrared surveys such as Spitzer, WISE, and SphereX, based on the hypothesis that other wavelengths may help predict AME, and other global parameters of the host galaxies. As AME theoretically needs ionizing radiation to spin up the dust grains, I will also include the ionizing photon rate calculated from the 33 GHz data. The regression model will first be trained on the 33 manually identified AME candidates, then tested on the full sample of galaxies. In addition to possibly discovering new AME targets, the results of my logistic regression model will better justify a sample of regions for follow-up observations with near-infrared telescopes such as the James Webb Space Telescope, as it is theorized that grains at 3.3, 3.4, and 3.47 microns are carriers of AME. Finally, this regression model could be an automated way to identify potential AME sources in the expected influx of data from facilities like the Next Generation Very Large Array and the Vera C. Rubin Observatory.